Hello everybody, welcome to second year physical chemistry. My name is Bernard Mostert. Today we are going to do a short review of the laws of thermodynamics. So what will be covered and why? We're going to cover the 4 laws of thermodynamics. You should know this from last year, and the laws of thermodynamics is of critical foundation for the rest of this course. If you do not get it, you are going to struggle. So, to help you along for this lecture, what you will need is a reminder of what is differential calculus. The nature of thermodynamics is that you have to know calculus. So, go over the things you learned last year. It will help you immensely. Lectures from last year I would suggest going towards is molecular driving forces and molecular interactions. And for looking up in the textbook, Atkinson's physical chemistry, I'm aware that people have different editions, so what I suggest is look up the following topics. The first law, and within the first law look at internal energy, state functions and exact differentials, and adiabatic changes. And then the other topic to look up is the second and third laws and the sections on entropy, the measurement of entropy, and combining the first and second laws. Okay, to start off with, I'm going to ask a simple question. What is thermodynamics about? And what I want you to do is pause this video for 2 minutes and write down your idea on what thermodynamics is all about. There's no wrong answer. It is important to cement in your mind what you think is happening and then see how it goes with the rest of the content. So, pause and restart once you're ready. All right. So I'll give you my definition of thermodynamics and what it's all about. Thermodynamics is the study of energy. Specifically, the energy associated with temperature and its effects on all other forms of energy. So, 2 big things to keep in mind. Energy and temperature and how they affect each other. Now, I'll make this clear when we start talking about the laws of thermodynamics. So, a brief review about systems and environments, and this is going to be important to understand the zeroth law. So in general, we have 2 things we worry about in the abstract. A thing called the system, which is something we want to understand. So here you can see a nice big picture. You have this system with the dashed box line around it. It's the chemical system we want to understand and modify. And then there's the environment around the system. And these 2 together becomes our universe. Let's make this a bit more concrete. Instead of talking about systems, we can think of a solution in a beaker. The solution can be our system, and then everything around it, which is the laboratory, together will form the universe. And so when it comes to thermodynamics, there's basically 3 key questions we're always interested in. What is the energy in and out of the system? Or in our case here, or example, the beaker, and with the solution. How are these energies affecting the system? How are these energies affecting the solution? And importantly, if I understand the first 2, can I manipulate the solution? Which brings us now to the zeroth law. So, you may wonder, why is this called the zeroth law? Back in the day, back in the 19th century, people were figuring out the laws of thermodynamics, and they figured out the first law, then the second law, and then the third law, and everything was wonderful till someone noticed that there's a very fundamental assumption missing. And this assumption is an absolute requirement in order to understand the first, second, and third laws. But by then, the laws of thermodynamics was pretty much well cemented, so they thought, well, instead of relabeling everything, we're just going to tag this one just in front of the first law. Hence, we got the zeroth law. Let's just hope someone doesn't discover the -1 law, because then things will just get ridiculous. At any rate, let's look at the statement of the zeroth law. If system A is in equilibrium with system B, and system B is in equilibrium with system C, then system A and system C is in equilibrium with one another. So this is all a lot of abstract words. So let's make it concrete and look at this figure we've got here. You have a beaker with your solution in it, and the solution is system A. And you have put a thermometer in your solution. You want to measure its temperature. So system B is the thermometer glass surface, and then you have the liquid inside the thermometer, which could be something like a colored alcohol, or if you have an older style thermometer, mercury liquid, and it will of course change its height according to what the temperature is in the solution. But note, when everything is sitting still or is at equilibrium, then your level of your thermometer doesn't change. But the assumption is that the temperature of your liquid is in equilibrium with your solution, but it has to go through the glass surface. So now you might see, so instead of saying if system A is in equilibrium with system B, you say if the solution temperature is in equilibrium with the thermometer glass surface temperature, and it is in equilibrium with the thermometer liquid, then the solution is in equilibrium with the thermometer liquid. And what this allows us to do is to define a quantity for equilibrium, which is what we refer to as the temperature T. Now, as a reminder, when it comes to thermodynamics, you always, when you do a calculation, you have to use the absolute temperature scale, which is usually the Kelvin scale. So whenever you do calculations, always make sure you go through Kelvin. Now on to the first law and thermodynamic identity. So the first law defines for us all the energies that go into a system. And most importantly, it defines for us the thermal energy. So here is the equation. You've got U, the internal energy. That's just another way of saying the energy of the system is the energy internal to it. And we're going to say we are interested in changes of the internal energy. So, because we deal with differential calculus, we're going to say the dU, or infinitesimal change of the internal energy, is equal to changes due to work plus changes due to thermal energy, or energy associated with temperature. The important thing to get here is that energy can be associated with temperature-dependent behavior. That is the power of the first law. It tells us that thermal energy is in fact an energy, and you can write down joules for it. The work, or dW, captures all other energies, which we normally can write down easily, such as mechanical energy, chemical energy, magnetic energy, electrical energy, gravitational energy, you name it. When it comes to reversible processes, those are processes that are in principle, you can go from one point to another and then back. You can rewrite this first law into what is known as the thermodynamic identity. And it's written as the change in the internal energy of your system is equal to mechanical energy, which is written as minus the pressure times the change in the volume. And we put a minus sign there to indicate that if the system's volume expands, it loses energy, but when you compress it, it gains energy. Plus temperature multiplied by the change in the entropy. That's your thermal energy. That's your reversible thermal energy. Plus this summation, which is essentially capturing all chemical energies. And we're going to have to get used to this, because this is what physical chemistry is about, is especially this last term. And we will get there trying to explain what's going on here on the last term. So, the energy changes in the system, or change in the internal energy, is the sum of all energy changes. So another way you can think about this is the thermodynamic identity. It's a way of doing energy accounting. We account for all energies in and out. And as I mentioned, there are many energies you can write down, but for chemical systems, these three terms are usually sufficient. Now, the second law. So the first law defines for us the energies, and especially the thermal energy. The second law tells us how thermal energy behaves while focusing on something called the entropy. Now, there are many definitions of the second law, but the following will be sufficient for us. The entropy of the universe never decreases. The second law will also give us the Clausius relation for the entropy, which is written here. It states that any changes in the entropy is greater or equal to changes in the thermal energy divided by temperature. And if you remember in the previous slide, for a reversible process, this relation becomes an equality only. You have an equal sign only. And then you can write dq equals t ds. Finally, the third law, like the second law, defines us the behavior of the thermal energy by focusing on the entropy component. So you should start to get the feeling that this thermal energy has a very important component to it called the entropy. Essentially, as we approach absolute zero, we approach zero entropy. So as we cool any system down from room temperature to almost 0 Kelvin, we will get zero entropy. But the problem is we can never get there. With this in mind, we can write down a very simple fact, which is the entropy S for any system is always greater than 0. Always. And that is it. So key concepts I want you to take away. You've got the zeroth law. You need an absolute temperature scale. There's the first law. There's two forms you can get it, write it down. The irreversible process, which just says changes in the internal energy is equal to the sum of changes in work and thermal energy. And then you have the reversible process, which is rewriting this all with utilizing the Clausius statement from just below. Brings us to the second law. The Clausius statement is the key I want you to take away. And the third law is entropy is greater than 0. All right. What you now need to do is, here's a quiz for you to go over. And the purpose of this quiz is simply to see, do you have some of the do you understand some of these very basics from this lecture? And I will see you face to face shortly. Thank you very much.